Welcome everyone to this lesson. Today we're going to be talking about graphs of normal distributions. We eventually want to get to the point where we can find probabilities under a normal distribution. For now, we're going to focus on getting familiar with what normal distributions are. Our goal for this lesson is to be able to identify the features of a normal distribution curve. Then we're going to focus on sketching normal distribution curves, including a special distribution, which is called the normal standard distribution. In this lesson, you're also going to learn how to use a rule called the empirical rule to approximate probabilities. So let's get started by talking about the features of a normal distribution. Many real-life scenarios produce a histogram that is going to be symmetrical, that is going to be unimodal, and centered at the mean. Here, we're talking about a histogram that has a symmetrical shape, also known as a bell shape. A histogram that is unimodal, that means it has one single prominent peak. And then we're saying that this histogram is centered at the mean, meaning that peak that we're going to see on the histogram is going to be at the mean. That is what we're seeing with the normal distribution curve that we have here below. We're going to use this as an example. Recall that mu is the population mean, sigma is the population standard deviation. I'm just going to write SD for standard deviation. And so notice, what are we seeing at the center? We're seeing the highest point on the graph at mu, which is the mean. So here I'm just going to write mean. I can also write mu, since we know that mu stands for the mean. On the curve, we're going to be able to see two special points, which are called transitional points. They are also called inflection points. So here we have what we call the hill, and then here I'm going to highlight what we call the valley. Now, the transitional points are going to be the points where the hill changes to a valley. So here we have the transitional points. The distance between the mean and the transitional point is 2 standard deviations. So notice what I have here. Okay. Notice what I have here on the horizontal axis. I have mu at the center. Then to the left, I went ahead and labeled 1 standard deviation to the left. That is mu minus sigma. Here we're simply saying take the value of mu minus the value of sigma and find that value which represents the first standard deviation to the left. We can do that again, subtract another standard deviation, that is mu minus 2 times sigma. This would be the second standard deviation to the left, and that is where we see one of the transitional points. Okay? Same thing here on the right. We can go ahead and label the first standard deviation to the right, that is mu plus sigma. And then we can label another standard deviation, the second standard deviation to the right, which is mu plus 2 times sigma. Here at mu plus 2 times sigma, we see the other transitional point. So again, here we're saying those transitional points are found 2 standard deviations away from the mean, on the left side and on the right side. Another feature of the curve that I want to highlight is that the area under the whole curve is equal to 1. And you can go ahead and give yourselves a drawing here. Go ahead and draw a standard normal distribution. What we're saying here is that if you were to find the area under the whole curve, this area is going to be 1. That is what we saw with the uniform distribution, right? If we're talking about a uniform distribution, the area under the curve is also equal to 1. So that is going to be the case with any distribution that we have. Now, if that is the case, right, if the area under the whole curve is equal to 1, then what is the area under the mean? Remember, the mean is right at the center of the distribution. So how much area do we have on the left side? We have half of the area, which is 0.5. Okay. What about the area over the mean or to the right of the mean? Well, we have 50% of the area, that is 0.5. Okay. So we are aware that there's symmetry in this curve, and we're going to talk about the symmetry later on when we talk about the empirical rule. Now, there's one more thing that I want to mention. We can go ahead and label more standard deviations to the left and right, as many as we want. Please note that the curve keeps going on the left and it keeps going on the right. One thing to know here is that the curve and the x-axis are never going to touch each other. We didn't see that with the uniform distribution, right? We saw values that could be between A and B. So we had a start and an end to the distribution. And let me show you over here. So the uniform distribution went from the value A to the value B. That is not the case with the normal distribution. Okay? Are we expecting to see values on the far left side and the far right side of the distribution? No, right? We are expecting to see values around the mean within maybe 2 standard deviations. If we see values that are more than 2 standard deviations from the mean, we call them outliers, right? We're not expecting to see values that are really, really far from the mean and to the right and really, really far from the mean to the left. But we're saying it is possible, right? We're not expecting to see that, but it's possible. There's a probability of seeing that. Now, I do have a quick note here below. The equation that creates the curve is f of x equal to 1 divided by sigma times the square root of 2 times pi times e to the power of negative 1/2 times x minus mu divided by sigma squared. Now, if you have taken calculus before, you might have an idea of how to find the area under this curve. That is not what we're going to be doing in this class, because calculus is not a prerequisite of this class. We're going to be finding the area under the curve using technology. So we're not going to be using this function. I just wanted to make this quick note. Okay. So let's go ahead and talk about how to sketch a normal distribution curve. And we're not just going to talk about how to sketch it. We're also going to talk about how to label a normal distribution curve. Let's look at this example. A random variable that is normally distributed has a mean of 3 and a standard deviation of 0.2. So here we're going to assume that we're talking about the population mean. So let's just go ahead and use mu. Here we're being told that mu is equal to 3. We're also given the standard deviation. We're going to assume that this is the standard deviation from the population. So we're going to write sigma is equal to 0.2. Now, this random variable, we can go ahead and say, let's just go ahead and call it x. Okay? So here we're being told x follows a normal distribution. It has a mean equal to 3 and a standard deviation equal to sigma. Instead of writing this sentence, I can go ahead and use the following notation. I can say x follows a normal distribution. We can just write capital N. And then in parentheses, we're going to write the mean and then the standard deviation. Okay? So here, again, x follows a normal distribution with a mean equal to 3 and a standard deviation equal to 0.2. So that is what that notation represents. You might see it later on your WAMAP homework or on other activities that we do in this class. So with that information, we can go ahead and create the curve. Here, I went ahead and sketched the curve for you. That way we are able to stay a little bit more organized. Here, we're mainly focusing on finishing this sketch, making sure that everything's labeled. If we're going to label this distribution, we're going to place the mean at the center of the distribution. Then we're going to label at least 2 standard deviations. So let's go ahead and do that. If I want to label the first standard deviation to the right, I need to go ahead and take the mean plus the standard deviation. Here I'm going to write 3 plus 0.2. If we go ahead and add those values, we get 3.2. So let me go ahead and erase. I'm just going to write 3.2. Now the second standard deviation here on the right, you can go ahead and take 3.2 and add another standard deviation. So add 0.2, or you can also use the formula that we had above where we said, take the mu plus 2 times sigma. That is the same thing as taking 3 plus 0.2 plus 0.2. If we go ahead and take 3 plus 2 times 0.2, we're going to get 3.4. So again, you can go ahead and do this in jumps. So 3 plus 0.2 gives you 3.2 plus 0.2, that gives you 3.4. Okay? So we can work a little bit faster if we just add sigma every time. Okay? Here on the left, we're going to subtract sigma. So one standard deviation to the left would be 3 minus 0.2. That is 2.8. Then if we want to label another standard deviation to the left, the second standard deviation to the left, we subtract 0.2. So that's going to give us 2.6. Again, I can continue doing this and I can go ahead and label more. Let's just go ahead and do one more. Why not? So go ahead and extend your curve. One more standard deviation to the left would be 2.4. And one more standard deviation to the right, the third standard deviation to the right, would be 3.6. Okay? Again, and we can continue doing this. Let me emphasize what we're doing here. We're learning how to sketch a normal distribution. We're learning how to use the mean and the standard deviation to create this sketch. We're learning how to label the mean at the center and then how to label standard deviations to the right and left. So we just got done with part A. In part A, we were being asked to label the center of the distribution and label at least 2 standard deviations to the right and left. Now, let's go ahead and talk about finding probabilities. Remember, this curve came from looking at a histogram. If you were counting frequencies or if you were counting relative frequencies on a histogram, you would be looking at the height of the bars, right? And it might be the case that you're looking at 1 bar or maybe 2 bars or 3 bars, right? So now when we're transitioning into talking about probabilities using a normal distribution, we're going to be calculating the area under the normal distribution. In part B, you're going to assume that you want to find the probability of X being between 2.8 and 3.2. You're not going to find the probability. You're just going to assume that you're wanting to find it. Now, what you're going to do, you're going to shade the area that represents the value of this probability. Okay? So let's look at our curve. Again, our curve is centered at 3. We have 3.2, 3.4 on the right. Then we have 2.8 and 2.4. If we're wanting to find the probability of X being between 2.8 and 3.2, that is going to be the area going from 2.8 to 3.2. That is this area here. So here we have a good visual of the normal distribution, and we also have a good visual of how we're going to be computing those probabilities. Okay? Now, let's go ahead and do one more. Assume you want to find the probability of X being less than 3.4. Shade the area that represents the value of this probability. Okay? Again, let's go ahead and label the mean and the standard deviations to the right and left. If we want to find the probability of X being less than 3.4, we're going to find the value 3.4 and we're going to shade the area below this value. And remember, this curve keeps going on the left and right. It keeps going and it never touches the horizontal axis. So we're also including that area all the way to the left side of the graph. Again, this keeps going towards negative infinity and positive infinity. We do have less area on the tails. So let me make a few remarks. When finding probabilities, if we want the probability of X being exactly one value, we're going to say that this probability is 0. Okay? So for example, if I ask you to use your curve to find the probability of X being exactly, you're going to say that this probability is 0. In this case, again, we're using area to find probabilities. And so if we're just looking at X equal to 3.5, we actually don't have any area. We're saying I would have to look at the list of data values. I cannot tell you what the probability of X being equal to 3.2 is. Again, we're saying we're just going to say that this probability is equal to 0. With that being said, the probability of X being between A and B is going to be the same as the probability of X being between A and B, including A and including B. Okay. So here we're saying the probability of X being between A and B, including A and including B, is the same as the probability of X being between A and B. Why? Because the probability of X being equal to A is 0, and the probability of X being equal to B is 0. So that's not going to change the probability. Okay? So it doesn't matter what notation you use. Usually I'm going to stick to just using this notation, the probability of X being between two values.